for the ins and outs of infrared technology. We want to thank the Industrial Heating Equipment Association, IHEA, and the Infrared Equipment Division, IRED, for organizing this webinar. And a couple of housekeeping items before I turn it over to the IHEA folks. The webcast is being recorded, including Q&A. So by being on this call, you are providing your consent to be recorded. And the webcast recording and PDF of the presentation will be also posted on EPRI's Program 199, the Electrification for Customer Productivity Program Cockpit for those of you from EPRI, and those who are from EPRI members. And that for question and answer, the preferred method is if you have questions at any time, you may ask it right then and there, or if you want to wait or hold till the end of the section to have your questions. Also, you may also want to, if you want to, you can type your questions on the chat window addressed to either Bhaskar Vairamohan or A.G. Nagar to ask the questions. And finally, if you could please place your phones on mute to avoid any disturbances to the presenters, that would be much appreciated. So with that introduction, I would like to turn this over to Kelly LeCount, who is the Education and Training Manager at the Industrial Heating Equipment Association. Kelly, you have the floor, please.
Thank you, Bhaskar. Good afternoon, everybody. We wanted to thank you again for joining us for the Ins and Outs of Infrared Technology webinar. It is presented by the Infrared Equipment Division of the Industrial Heating Equipment Association, which is also known as IRED. We'd like to also thank the Electric Power Research Institute for hosting the webinar. Their support makes this possible to offer this information to the attendees. My name is Kelly LeCount, and I'm the Education and Training Manager for the Industrial Heating Equipment Association. If you're not quite familiar with IHEA, it is a professional trade association representing the major segments of the industrial heat processing equipment industry. IRED provides services and resources to our members that help enhance their ability to serve the end users in the industrial heat processing industry. And just again, a reminder about taking questions. You can type them in the chat box, or you can ask questions along the way during the webinar. Next, I'm going to introduce all of the speakers up front and give a little background on them. Our first speaker will be Michael Stowe, and he is an energy consultant with Advanced Energy. Michael's a senior engineer on the energy engineering team and focuses on process heating and energy efficiency in manufacturing plants. He has over 27 years experience in the manufacturing industry in positions such as design engineer, production manager, plant engineer, and facilities engineer. Mike works with utilities, process heating equipment vendors, and manufacturing plants to find the best technical and energy efficient solutions for industrial processes. Michael will be presenting the basics of infrared. Next on the list would be John Podak, and he is the Application Sales Manager at Fostoria Process Equipment, a division of PPI Corporation. John has been with Fostoria Process Equipment for over 40 years. He has proven expertise in the industry with his vast knowledge of ovens, control panels, and equipment testing, and continues to deliver excellent service and training. He's built ovens and control panels, provided field service, served as lab manager, regional sales manager, and senior application sales engineer. John will present the electric applications of infrared. We'll also hear from Mike Chapman, the global product manager for Heraeus Nobolite America. Mike founded Vulcan Catalytic Systems for applications in the plastics industry, which later progressed into the finishing industry, where the catalytic heaters that power the Vulcan ovens are used for drying, gelling, and curing powder on metal substrates, as well as heat-sensitive substrates such as plastics, MDF, and other engineered wood products. In 2014, Vulcan was acquired by Heraeus Nobolite to expand their process heating portfolio to include both gas and electric heating systems for industrial applications. Mike was educated in the UK, graduating in ship science studies, and has a number of patents in the process heating industry. Mike will be telling you about infrared gas applications today. So those are our three speakers, and I would now like to begin the webinar educational portion, and Mike Stowe will start with an introduction to infrared technology. Michael, are you there?
I'm here. Can you hear me?
Very good. Take it away.
Okay. Today we're going to talk first about the basics of infrared and then some applications. So we'll let's see. I have control now. Yeah. Okay. So we're going to talk about what is infrared and how does it work, and then we're going to see some of the things you can do with it. Infrared basically comes from the Latin word infra, for meaning below or under. And, of course, red is the color. If you remember back in high school or physics class, Roy G. Biv is the colors of the rainbow, which is the visible light spectrum. And R, or red, is the lowest on that spectrum, and infrared is under that. So on the electromagnetic spectrum, infrared is right beside the visible spectrum. Infrared's invisible, although you do get light from infrared elements very frequently. There's many names for infrared. You hear it called many different things: radiation heating, radiant heat, infrared, IR, thermal, infrared light, all different things. But typically there's an orange to yellow glow and significant heat that you can feel radiating from an infrared source. Just a brief look at heat transfer, because this is how we need to talk about infrared basics. If you think about a campfire and you put a poker in the fire that's metal, it's going to get hot. The heat is going to work its way up the metal, and eventually if you grab that poker that had been laying in the fire, the end of it could be very hot, even though it wasn't in the fire, because the heat conducted up the length of a steel poker. That's conduction. It needs contact. Convection is like holding your hands above the fire and feeling the heat rising effect. And then radiation is when you're off to the side and you can feel that heat from the glow of the coals or the flame, but you're not actually touching the flame or in the coals. So a little bit more on these. Conduction is an internal process. As you can see in the little picture, there's the hot fire on one end of the poker, and that causes excitation of the atoms, and that heat will gradually move down through internal contact. But looking at the poker itself, you don't really see anything moving. It's an internal process for conduction. And conduction can be important with infrared use in a curing process. We'll see that later. Convection is like, just think about a typical convection oven that you could have in your kitchen, or a natural gas convection oven, just a typical furnace. You have a heat source, and it could be electric, it could be natural gas, but then you move that heat, you blow that heat, you force that heat. You can have natural convection, which is like heat rises and cool air sinks, but forced convection is typically a process we see, and it's an external process. It acts on the external part, or the external part of a turkey in an oven to cook it. So that convection requires some motion, and you heat all the air and move the hot air around the item to be heated. Radiation, which is IR, is the third method of heat transfer, and that is the electromagnetic spectrum. If you remember, we talked about the visible red, and infrared is to the right of that. There's no medium needed. If you had to have a medium or an atmosphere or something to move radiation, the heat from the sun would not get to the earth. But the heat from the sun travels through the vacuum of space and gets to the earth with plenty of heat still in it. And the heat comes out upon impact. So infrared rays from the sun impact the earth and heat it up. Infrared light or infrared heat from a heating element impacts the part, but it doesn't have to heat all the air in between. It heats the part when it contacts the part. And we'll see a little bit more about that in just a minute. Here's a little more detail of the electromagnetic spectrum. You can see the infrared broken down. It's right above the visible spectrum, which is what we can see with the naked eye. And infrared basically is broken up into three sections: short wave, medium wave, and long wave. Each have different benefits and different applications, which we'll talk about with the other speakers. Basically, what happens is the wavelengths within infrared have a color associated with them. You can get light from the heating element, from an infrared element, and you can kind of see how the color changes and the wavelength changes from short wave up to medium up to long. Long wave is more like a sine curve, more open and tighter and very tight wavelengths for short wave. Short wave has a very bright yellow to slightly orange light. Medium wave is more dull orange, and then long wave is almost dark blood red to black. Here's a few characteristics about infrared. Again, not all infrared is created equal, and you can target your infrared heating wavelength to suit the product that you're going to process. If you need a short wave or a long wave, the infrared equipment manufacturers can help you determine what's best for your process and your application. The short wave is very, very hot, 4,000 degrees Fahrenheit at the source, very short wavelength, and response times are very quick. You turn on a short wave infrared heater and it's going to heat in seconds or less than a second. Medium wave, little less heat, little bigger wavelength, and a little longer heat up time, response time. And long wave is just the same direction, a little cooler, still hot, but cooler than a 4,000 degree short wave, and it takes a little longer to respond. So you got short wave is hot and fast, up to long wave, which is not as hot and a little slower. And here's a graph of those same characteristics. Going from 100% to 100% available energy from the infrared source, you can see the short wave gets to 100% output in a matter of seconds. Medium wave takes a few, maybe a minute or half a minute, minute and a half, and then long wave takes up to 4 or 5 minutes. So processes that need fast, hot would tend themselves toward short wave and vice versa. Here's just some examples of some different emitters. In the upper left-hand corner, electric short wave, you can see the bright yellow light. The gas catalytic long wave, that's a gas catalytic where you're generating the infrared from natural gas instead of electricity. It has kind of a dull yellowish red color to the elements. You have a medium wave gas generated infrared heating element in the bottom left. And then you have a full circle, almost like a stop sign, an octagon of infrared elements that are medium wave, very orange. You can see the gas medium wave and the electric medium wave. The color looks almost identical, and you're just using a different source of energy, gas versus electric, to create the infrared heat. So just a quick review about what is IR. It comes from the Latin infrared. Infra means under red on the electromagnetic spectrum. The heat transfers by radiation, which is a line of sight to the part from the heating element. It's part of the electromagnetic spectrum. We mentioned that, and it comes in a variety of wavelengths that you can make use of depending on your special application or product shape, size, or configuration. So you got short wave is very fast and very hot. Medium is pretty fast and medium hot. Long wave is a little cooler, still hot, and a little longer. So let's talk about infrared and how does it work. These three pictures on this slide are taken with an infrared camera. The first one's a little mouse. The second one is a three-phase electrical circuit. And then the third one down at the bottom is a building. And you can see the windows have much more heat transfer than the building parts. And you can see the mouse is giving off some heat. And one of the three phases is a little bit hotter than the other two. So infrared is very easy to detect. There's all kinds of infrared cameras, and it can be very useful. But everything with a temperature above absolute zero, anything with heat, a temperature emits some infrared energy. Human bodies do, electrical wires, anything that's hot heating duct inside of a building, an oven, buildings, just looking at the envelope of a building. The higher the source temperature, the more energy that's emitted and more intense it is. So a mouse is going to emit infrared energy, but you can't cure powder paint with a mouse. Heating element, intense shortwave, we'll talk about that. And it requires a line of sight. That's not necessarily a limitation, but to get the heat into the part needs to be seen by the element. But if there's a blind corner, that can be heated through conduction. So what happens when this is how infrared works? You have your infrared emitter. This can be a gas catalytic, or it can be an electric. It can be shortwave or longwave. But this is what's going to happen. One of three things. The infrared is going to travel in a straight line, and then it's going to impact the workpiece. In this case, it's a big flat workpiece. And one of three things is going to happen. The infrared is going to go straight through it, or it's going to reflect right off of it. If you think about trying to get infrared into like a shiny piece of aluminum, that could be a little more tricky than a black, something or darker, or it's going to be absorbed. The absorption is the key. So what your equipment guys can help you with an application is to find the right wavelength and the right configuration of the elements and the right heating levels so that most of the energy gets absorbed, so your part will get hot. You don't want to have it blasting through there and 90% of your energy being transmitted or 90% of it being reflected. You want to optimize your infrared heating element to your part so that most of the energy is absorbed at the proper level. And again, the energy source can be natural gas or electricity. So for an object to be heated by infrared, part of it has to be absorbed. If there's no absorption, it's not going to get hot. If it just passes through it or reflects, it's going to be very limited heating. An object must absorb some of the infrared energy to heat up. So the things you need to worry about or think about that the equipment vendors for IR can help you optimize is what wavelength makes sense, what temperature, what shape. You can see in the picture that you have elements all around, so you're going to be hitting the part from all different angles. And the other good thing with the IR is you can, for example, if the part was denser or had more mass up at the top, you could make these upper elements on longer, and maybe the side one's not quite as high, and so forth. So you can do a recipe for a given part. But picking the wavelength, the temperature, the shape of the emitters, their orientation toward the parts, and then of course the bottom line is you're going to want to run tests. You're going to want to test and make sure the configuration works the way you want to. Boltzmann's law, this is not something you need to try to, we're not going to try to do any math today, but the whole point of this is just to show you that the power from infrared is proportional to the temperature to the fourth power. So there's some Stefan's constant, the area, the emissivity, and the temperatures. But the bottom line that I would like you to get out of this is if you double the temperature, you get 16 times the power. Okay, so the fourth power, 2 to the fourth power is 16. So you really get with a little bit of temperature change will give you a lot more energy transfer with infrared. Just a few things about the emitters. Again, we talked about shortwave, and here's some examples. Very hot, very fast, up to 4,000 degrees heating elements. Can heat up very fast. They're pretty much instant on, instant off, which can be very good for production or changeovers, and very fast response time. Medium wave emitters, again, they're more down in the orange color range, 1,800 degrees, typically pretty fast heat up rate still. And then you got your long wave, which are more of the dull red, lower temperature, but some processes don't need high temperatures. Heat up still fast compared to a natural gas convection oven. So a quick review of how IR works. You need a line of sight. All the emissions from IR, remember this is important, they're going to be reflected, transmitted through, or absorbed. And absorption is the key to getting heat into your product from an infrared source. The energy source to create the infrared can be natural gas or electricity. And there's a very wide variety of emitters, arrangements, sizes, recipes, programming that can optimize an infrared oven to your parts and your variety of parts. And the IR equipment vendors can really help you optimize your system to match. Here's just a few factors. I'm not going to read all this, but some of the things you want to consider when you're selecting IR is the total output you need, how far should you be from the emitter, what are the reflective characteristics. Are you trying to infrared heat something that's black or very dark in color, or are you trying to infrared heat a mirror, something that's very shiny and reflective? Is there air movement, or do you need a little air circulation in here? What's the ratio or the aspect ratio? Are you trying to do like a sheet of plywood, or are you trying to do like a block, a cube, something that's very thick and solid? All those factors need to be factored in to your process. Some typical applications, and this is the guys are going to take off on this next, but there's just a few of the things you can do with this. That one picture is a thermally formed laminated floorboard for a car that you use infrared to heat this up and then mold it to this shape. And then there's dozens of others beyond what's just listed here, but those are some of the main industries that do use infrared. So just a basic review, infrared is the under red. It's part of the electromagnetic spectrum of radiation. It's very fast and very efficient. Almost 98 or 99% of the energy for electric heating elements are converted to heat. And there's very flexible applications. It's nearly unlimited. You just need to get with your IR original equipment manufacturing vendor and test it. But you can arrange the elements geometrically. You can set the heating, the timing, the geometry, and you really can optimize that for any given part. So the applications are literally just about unlimited. And that's all I have. John Podak is going to talk about electric infrared applications now.
There are companies that we're going to hear more about. They put these products out.
John, are you on?
Hello?
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 We hear you now.
Okay, I was on. I don't know what. Okay. This first picture that I'm showing here is inside of a convection oven that these springs are typically cured with hot air. They were having problems and they wanted to speed up their line. They didn't want to expand the convection oven because it was expensive and they needed more floor space. So in a lot of applications like this, we will run some lab tests, and we decided how much infrared we needed inside this convection oven. So we installed the infrared inside the oven walls. We took up no more floor space. We were able to, if you look at, the convection heat was set at 450 degrees. We were able to turn that temperature down, so we were saving some gas on the convection side. And the other thing to consider when you're putting electric infrared inside of a convection oven to do a boost like this, that every bit of energy inside of this oven becomes 100% efficient. So all the energy that's in there and created from the elements and bounces off the product getting hot stays in the airstream. This next slide is a temperature. One of the things Mike said that the energy from the distance to the emitter to the product is to the fourth power, and this is a good example. If you look over towards the end of this line, you'll see that some of the springs, which is the hottest one, up in the pushing 400 degrees, is the spring side that's closest to the elements in that previous picture. And the other one's the one in the center. This customer did not want to change how he loaded these and hung the springs on there. But and then some powders have overbake in them. So this here, we had an 100-degree differential, but there's a 100 degree overbake in the powder. And keep in mind, all we're trying to do is speed his process up, get more heat in his product faster in the first part of his convection oven, and then the rest of the hot air in the convection oven will normalize this. At the end of this process, these temperature curves come together and it finishes out his project or process. So what we were able to do here in 2 minutes and 23 seconds was speed his line up and create the production that he was after in this process. This next process is something that we do, and through lab testing stuff, we found that a lot of times the short wavelength T3 quartz lamps work for this, and we're curing water-based lacquer finishes on cabinet doors. And we also do the stains, the sealers, the coatings, and stuff like that. And keep in mind that when these elements are in front of these heaters, the parts maybe get exposed for 20, 30 seconds at the most. That's all it takes sometimes. Again, lab testing and making sure you know what the product is, the different stages of stains and sealers and top coatings and stuff in this industry. But it doesn't take a lot of time to do a lot of this stuff with hitting it with infrared. It just needs the right wavelength that works well with the application. So again, lab testing. This next application is a rubber, water-based coating, again on extruded rubber seals. They're running this rubber seal like a door seal on an automobile. They run it at 30 to 80 feet per minute. Again, this is rubber, and it's black, and it heats up really quick. And if for some reason the line stoppage of the rubber seals going through here would stop, it would burn up in the intense heat that we have in here. So again, we chose shortwave quartz lamps because of the fast response time. So it's so this thing heats up and cools down. We reduced our cycle time from minutes to less than 30 seconds, depending on what seals they're running through this oven. I like using this next application because of, one of the things Michael said, you can zone an oven. this here, we're curing powder on fire extinguishers, and on the bottom of the fire extinguisher is the coupling welded onto it. That's where the most of the mass and the heaviest metal is, and as you can see, we have more heat turned on to get the bottom hot, less heat on the sides, and we've got a zone in the top. And typically in an application like this, we design the oven so that we have a build and a hold zone. In this case, we're building the heat with shortwave infrared and holding with medium wave. We have 3 zones in height and in 2 zones in length, and we're doing a full cure at 375 degrees. And this next one is the temperature curve coming off these parts. You can see how by zoning, how you can keep the areas, you got thermocouple on the base, on the side, and on the neck of the bottle, and how they all come together. We boost it for 80-some seconds. We hold it for about 1 minute and 40 seconds, or 140 seconds, and then we end up with full cure. One of the things to make sure, though, this was all done with full buy-in by the powder vendor in this case. You need to make sure, because the powder vendors, some of the powders say on the side of the box that they need substrate temperature of 375 degrees for 10 minutes, possibly. Could be a typical structure. So what you need to do is have the powder vendors and any coating vendor present when you're running lab tests to get buy-in on the process you're doing, because in this case, we got full cure. It passed the 50 double rub MEK, the crosshatch testing, and we had no problems with it. So again, this is the reason we run lab tests, so we can speed up processes for people.
The 50 MEK cross testing.
This next application's kind of a infrared vendor's dream. It's a thin metal part with black powder on it. Again, we're getting full cure in less than 3 minutes of heat time. So, the mass of the product isn't that great. It's got quite a bit of surface area on it, and it works very well with infrared versus having a convection oven. You'd be in a convection oven 20 minutes. You're in here 3 minutes or less. We're curing a powder on an aluminum wheel, and there's a base coat, a clear coat, and some wheels are polished and have just a clear coat on top of them, and we're doing it in less than 10 minutes. And I guess one of the things that we'd like to discuss when we're doing this is Michael talked about how infrared will reflect off of polished and highly polished objects. And in this case, what we're actually doing is the clear coat powder is opaque, kind of looks white when you spray it on. The powder actually absorbs the infrared, and then it conducts into the aluminum wheel. And then all the nooks and crannies in the aluminum wheel, because aluminum conducts energy so well, goes around. So that's why line of sight in this case, and conduction, and the fact that the coating is absorbing some of the infrared helps and speeds this process up. We're in a convection oven, again, it'd be 30-plus minutes, and we're doing it in 10 minutes or less. But it can be done. I guess, again, lab testing is the key. Here's a high-density infrared oven. We're preheating a steel web. This product that runs through these ovens is running at 225 feet a minute. In this oven, it's only 38 inches of heated length in it. We see the product for 0.84 seconds in this thing. We're trying to get a product temperature from ambient to 160 We're using 100 watts per square inch of shortwave infrared. Again, shortwave because we need the response time. And what we're trying to do here is heat the surfaces of this product, the coil going through it, so that it is a little more pliable. The coating is pliable, and also the metal's got a little bit of temperature in it, and it goes through the roll former better, and it doesn't. The edges of the coating does not going through the roll former doesn't crack or create problems, and it also has found out another benefit by having the warm go through the roll former is that it's a little less wear and tear on the equipment. Here's something that's we're curing powder on the automotive seat springs, and this application, all we're doing is curing the powder where they had, because these springs were actually already coated, and they cut them into shorter lengths for different vehicles and different types of seats, and they were E-coated, and what they're trying to do is where they cut these things on the bottom little tip is actually just cure that. So what we're doing is, this is a shuttle of indexing oven, and the heat comes up and just heats the tips of those things. It goes back down out of the way. The next one indexes, and when it goes to the next station, it's a fluidized bed of powder, and then it gets the powder on the hot part, and then it goes into another section that actually cures that powder. So it's an indexing type thing, and all we're doing is curing the little tips of these things so they don't rust with the powder on it. So it's little spot things you can do. In a convection oven, you would have to heat the whole thing back up, and all that energy it would take to do it, and here we're just heating the tips of these product up just to do exactly what we want to do with it. Here we're what we got is an infrared batch oven, which most cases you see a batch oven, it's convection, but in this case what we're doing is curing just flat sheet metal panels on parts, for a customer that's, had to take and heat up his big batch oven to run all his little sheet metal parts on it, and it was taking him a half hour, 45 minutes to get up to temperature and cure it. And we found with lab testing that we could get this done in 5 minutes, and it's not it's only 6 watts per square inch of emitter, medium wave infrared. It doesn't take that much, but the parts will get up to temperature and cure in less than 5 minutes. And also we can, as Michael had said, we can use infrared to do curing, and we also use it for water dry off. We have customers that we're using medium wavelength quartz tubes. We introduce a little bit of air in through the reflectors, and we're doing full water dry off on these parts in 1 minute, and we're getting a full infrared cure on these parts in less than 2 minutes. And this line's running at 18 feet a minute. He's got 18 feet of dry off oven. He's got 36 feet of powder cure oven, which we divided that into 2 zones in length so that it's 1 minute to get to temperature, 1 minute of hold, and he's getting full cure on a lot of his sheet metal parts. And in this next slide, what I want to show you is this guy also, he's a job shop. So this is that oven, the 36-foot length of it, but as you can see in the bottom picture on the right, we have made this so that he can run a 2-foot part window, or he can roll these banks out and have a 4-foot part window. If he gets a bigger, heavier, more geometric shaped part, he can roll the banks out, have a bigger part window, and slow his line down for the bigger parts. And when he's running his little flat sheet metal parts, he can push the banks in, so he's got the smaller part window and run the parts a lot faster at the 18 feet a minute and get a full cure in the 2 minutes. This is a typical web application. We're heating automotive carpet. We heating carpet backs. This is a fast response medium wave heaters that run up to 40 to 50 watts per square inch of emitter surface temperature. Again, some of these emitters are a fast response. They're not as fast as a shortwave lamp, but we needed to get all the way across this 6 and 8 foot web. Notice that the back side of this is a reflective material, and we run the web beside it. So anything that does go through some of this carpet, there will be some energy go through it because it's got a little bit of porous in the needling on it, and so it'll reflect back on the carpet itself. So keeping the inside walls of any infrared oven reflective so that the energy can bounce all around is a good thing to do. So here's an application where we're actually heating aluminum engine blocks, shiny aluminum engine blocks. We're using a fast response medium wave infrared for this. It does have a little better convective build in it. We're heating these engine blocks so they expand, so they can put the sleeves in them. But we're doing this in a 10-station oven. Each station's about 40 seconds. So we're not, in a convection oven or a furnace, it would take half hour, 45 minutes, and we're doing this in less than 10 minutes, heating this whole block up to 400 degrees F. So again, with lab testing and stuff, infrared can be an alternate to any other processes. Here's one that we're doing. You would think you would need a furnace to normalize metal on huge crankshafts, but we're using medium wave infrared in this application. The crankshafts are hanging, they're coming off all their lathes where they're turning the journals on them, and where those get hot, they need to normalize all the metal in the whole thing so they stay straight. Usually they put these on racks and then put the racks in a furnace to do this. We're getting, what they found out is when we're hanging them like this, they actually end up being straighter than sitting on a rack because they're only supported in two places on a rack, and here they're hanging down. But we are able to get the 550 degrees in this oven with medium wave quartz tubes that run color temperature about 1600 degrees with a aluminum silicate board design inside this oven. And that's all I have. Just enough applications to maybe spark some interest. So if there's any questions, we can take those. If not, we're going to go on to Michael Chapman, who's going to show some gas catalytic applications for you.
Thank you, John. While Mike is getting ready, I just want to kindly remind everyone to put yourself on mute unless you have a question. There was some background disturbance and noise, so appreciate that. Thank you.
Yes, hi, John and Bhaskar. Steve Briggs here for First Energy. Appreciate the overview. I thought this was very helpful. Appreciate both of your presentations. I had a quick question on applications for like drying. We've explored, folks that are trying to dry out like wet paper or wet mix, that kind of thing, and have been told that even though I know there was in some of the applications paper was listed, I've been told many times it's maybe not a good application. Can you explain that further? Is that just not being absorbed, or does that work? Maybe you could kind of explain. I know it works well in powder coating and wet paint curing and so forth, but just a perspective on paper drying or that type of thing.
Actually, infrared loves water. It absorbs water, and Michael's going to show probably, I think, I haven't seen all his slides, but talk a little bit about that even with the catalytic. If anybody's from the north and see Fostoria heaters out around up in Chicago at the airports, we melt snow with them. So, it's all in lab testing. A lot of times when they're doing paper pulps and stuff, it's so wet that it's just crusting maybe the surface and not getting down in it. But if there's anything thin with a moisture on it, drying veneers, wood veneers, We take the extra percent out in like 0.3 of a second, take an extra 3, 4, 5% moisture out of a 1/8 thick wood veneer off of a sheet of plywood. So it does medium wave, especially they say, but infrared does like water and it absorbs, and that's why I showed the application for water dry off of parts instead of using convection of them.
Thank you, John. I may follow up with you directly on some specifics, so appreciate it.
Okay.
Okay, so this is Mike Chapman. I'm going to proceed here, if I can. Gas infrared applications. And so what I'd like to do is to get started is just to explain a little bit about catalytic reactions, because it is different from electric infrared heaters. We basically have a catalytic reaction that takes natural gas, or sometimes propane, in the presence of oxygen and a hot platinum. We get a chemical reaction that gives off carbon dioxide, water vapor, and heat. And it's that heat that's generated from that chemical reaction that we're using as infrared. Surface temperatures can range from 350 to 900 degrees F, depending on the volume of gas that is being put into the heater. And there are some special properties from the infrared in the way it's diffused as it is coming out of this cloud of hot gases, if you can imagine that. And the reaction sites are right on the surface of the heater, so they're coming out in what we sort of term a hemisphere in all directions. So we get a multiple diffused infrared coming off the surface of the catalytic heater. Let me just do this here. And so the process requires the platinum to be at around 300 degrees Fahrenheit. So we have to have this electrical preheat, which is buried inside the heater. That is on for approximately sort of 15 minutes. We need an electrical preheat of 15 minutes. We have a safety device in the back of each heater, because we don't have flame safeties since there's no flame in the system. So once the thermostat switches all closed, then we know that the catalyst is up to temperature and ready to receive the gas. And the gas comes on. We keep the preheat electric heaters on for approximately 3 minutes to really get the catalytic reaction established at that just below the surface of the heater. Then after 3 minutes, the electrical heaters drop off and then into the normal gas pulsing system that we have. The dispersion plate in the back of the heater has got a lot of small holes in it that evenly disperses the gas throughout the entire surface of the heater. There's a slight pressure drop between the very back of the heater and atmospheric, so we do get good gas distribution at low fire as well as high fire. So it's a little different. It takes about 25 minutes total there to get the heater system up and running, but once up and running, it's the preheat goes off and then it's just running on pure natural gas or propane. Some of the properties of heater, the catalytic heater, the one thing that the long wave that Michael has talked about before is we consider it to be colorblind. Long wave cannot really recognize yellows, reds, blacks, whites. It treats it all the same as a sort of an organic coating. The surface temperature, I say there, can range from 350 to 900. It is a true flameless reaction. That's sometimes a little difficult to understand how you get the full BTU content out of gas without a flame. But catalytic reaction is completely flameless. In fact, we're approved for factory mutual for heating hazardous heating areas, which would, in layman's terms, comes down to an acetone storage room. That's just how safe they are. They are, as stated by factory mutual. We have an even heat distribution across the surface at all levels of firing. Michael was saying 5 minutes response time. We like to think it's a little less than that. From our technology, we can do it in sort of 1.5 to 2 minutes from low fire to high fire. So we are reasonably quick, and the controls allow us to do that. Safe emissions from CO2 to water vapor, and there's no NOx or CO emitted from the chemical reaction. Okay, some of the applications that we're involved in, starting up at the top left, this is a drying application. John Podak mentioned earlier, infrared is a good absorber, is well absorbed by water, and typically in the dry-off situation, the parts have gone through a phosphate or some type of cleaning system and a rinse, so that basically leaves what is generally a film of water over the part, and that film really absorbs the long-wave infrared very, very quick, as well as short-wave, but long-wave seems to work very well, especially at the speeds that most finishing lines are operating at. Have to be careful a little bit about drips and making sure there are holes in the right place to get the water drained out of the part, but it's a very efficient way of drying. The tank industry has been quite, we do quite a bit of applications in that, both liquid and powder. Fire extinguishers, scuba tanks, there's actually scuba tanks in operation there. Full cure oven, the one to the right showing the blue parts is, again, a full cure oven for those actually parts that were washed on the left. The wheel industry is another area that we do quite well in. Difficult part to heat from an infrared, but if it's surrounded correctly by the heaters positioned, for these particular applications, we do get very, very good transfer of infrared and get it actually into all the nooks and crannies of the part. And the tank, again, the propane tank industry has been, on the left-hand side there, has been a product that we do quite well with, especially in refinishing. There's a lot of propane tanks that get refinished. Material handling, long, skinny metal parts, all different types of metal tubing and flat parts, axles. It all works very, very well with infrared. It just, again, it needs control of the oven, top to bottom heating. We adjust the heaters, more heat at the bottom, less heat at the top, and also more heat at the beginning of the process, and then back the heat off towards the end of the process, just to ramp the temperature up and then maintain to get the full cure. The bottom right-hand one is actually a gel application for ceiling tiles, metal ceiling tiles in the UK for this one, where we're actually gelling the parts prior to going into the convection oven. Advantages here is, we rapidly increase the surface temperature, fuse or gel the powder, and then once it gets into the convection oven, the powder is sealed and then you can actually increase the volume turns within the convection oven to increase the velocity of convection, which is how the more efficient way of getting the heat out of the hot air is by increasing its velocity and how it impinges on the part we're trying to heat. So adding gel ovens up front of convection is really helps the efficiency of curing all the way down the line, and allows you to actually shorten your footprint. So either inserts or exterior infrared applications for convection it's like the belt and braces approach to curing. Again, the same type of thing is we look at these, we arrange the heaters completely around the part to describe what we call a ray trace. And again, the heaters are interconnected with galvanized sheet metal, which is a complete reflector for infrared. So if the infrared misses the part, hits either one of the opposing heaters, it's absorbed and eventually gets radiated, or it hits the galvanized surface and is immediately popped back at a different angle. So the infrared gets completely jumbled up in all kinds of different diffuse patterns within the oven. And again, it's top to bottom control is required. Again, this shows a couple of different applications. Far right is a gel oven for large washing machine type parts, where again it's gelled prior to going into the convection to prevent contamination of parts, especially if you have fast color changes on the line. You can put black and right before white and not get any contamination so long as the powder is gelled before going into the convection oven. The one in the middle is for a prop shaft application. Again, it was a full cure application for powder. The one on the left, we actually turn the horizontal heaters, put them vertical, and arrange them in an accordion style. This is for powder coating MDF, where it's important to be able to attack the edges of the part, the leading and trailing edges, where we have to get the heat into before it gets, or as it's going into the side surfaces. So it's just a question of arranging the emitters to attack the part and direct the energy exactly where it's needed for the process. again, as you can see, in all those ovens, we all use this galvanized sheet metal as a means of anchoring the heaters. There is no gap between the heaters, so the infrared is completely contained within that space. And as a result of that, we don't actually need insulated panels on the outside of the ovens, because all the heating is done right in the halo within that ray traced part window. This was just back to that application of fire extinguishers. Again, in this piece, we actually rotated the parts as they went down just to make sure we did get even curing all around the parts. Tanks sometimes a little thicker at the bottom and at the top, so extra heat is sometimes required in those places. And the way we start the whole process is to design what we call a ray trace, where we group the heaters around the part window. Sometimes they're tall, sometimes they're skinny. It just depends what the object, how it needs to be heated. This is an application that was, again, this was in the UK, where we had a customer who was making 6 or so or 8 of these step ladders a day. He would send them off to a custom coater and then have to wait a week or so for them to come back. And he decided to put his own small powder coating line in. And in this case, the infrared oven is only 7 feet long. And so once it was powder coated, it was actually advanced through this oven at about 6 inches a minute. So every part of that step ladder would be in there for approximately sort of 14 to 15 minutes. And with control from top to bottom, we could really, adjust where the heat was needed, during that whole process. Net result was the customer could powder coat all his pieces in the same day and actually get them off to the customer. So his all the amount of money he had in inventory was reduced significantly, and it was a just-in-time delivery for him. So we believe that infrared is one of the key parts towards a lean manufacturing or curing process. So it's all part of the infrared story. Low bake powders are really becoming ever more popular now, especially on MDF. And it's a really good breakthrough for us. We're actually down in the curing temperatures to around 250 to 270 degrees Fahrenheit for 3 to 4 minutes. Can be a 1-coat or 2-coat application. It can be textured, smooth. Extremely high elongation in these powders now, so any edge cracking is completely eliminated. The design of the oven ensures that these edges are really well cured. That's always the issue with dealing with these engineered wood products. The whole process is now very competitive against thermofoils, and so there's a big move now into the kitchen cabinet market that we're working with. Some very large furniture manufacturers in Europe have adopted this process, and it's been very, very successful. But a number of these systems operating around the world, and it's really starting to take off now. And it is possible only really possible with infrared. In the early days of MDF, it was done through convection ovens, and that was just basically a disaster. It was doing more damage to the MDF. With infrared, we're only heating the surface, so the core of the board is not getting to any of those elevated temperatures where the internal resins can break down. And here's just a typical picture of on the left is a preheat of the MDF. It needs about a 1.5 minutes preheat to make it conductive, and then it actually acts like a piece of metal as you apply the powder. On the right-hand side is just a typical racking for one of these large furniture manufacturers in Europe that we have operational now. So it's a very, very robust process, and infrared is the absolute key to it working correctly. Here's in a nutshell, the process of preheating or for heating MDF. We need that 1:15 preheat. On the left-hand side, then it cools down just a little bit during the powder application, and then jumps into the infrared oven, and then you see the rapid increase of temperature of the surface and the leading and trailing edges all the way up to the top, and then we maintain that temperature about 260 or so for 2.5 minutes. It's cured, and then the cool down starts. So that's the process. It's very, very short, and it's very kind and friendly to the MDF. while getting a full cure all over the part. An area that I'm not overly familiar with, but gas is still used in high radiant gas burners, and these tend to be much hotter surfaces, as John and Mike have mentioned before. And they're definitely in the medium wave. They tend not to have quite the same turn down that we can get with catalytic. However, they have their place in the infrared market and in powder coating, so it's something that should always be looked into, depending on what the application is. They tend again to be a little bit more dense in their BTU consumption on a per square foot basis, maybe a factor 3 to 4 times what the catalytic is, but that can have its advantages, especially if you have fast moving lines. That paper line that was discussed earlier, this may be one of those ways of putting some extra BTUs into it. And again, on the water drying, as John said, infrared is very well absorbed by water. It really does dry very quickly, and it's just a question of matching the BTUs required to dry the certain weight of water off in the process. So that's I think the story with infrared and water. It is the most effective way of doing it, so long as the process can handle it and the paper's not falling apart. I think that's it. Thank you very much. Again, if there's any questions, there's my email address. I'm available for questions, and I think I now pass it back to you, Bhaskar.
So thank you, Mike. I'm going to turn it over to Kelly just for last minute comments while you gather up some questions for the speakers. So Kelly, I'm going to give the floor to you for a few minutes for the closing comments, and as we get any questions, we will start asking them in a moment. You can, those of you on the phone, if you would like to ask questions, you could ask by unmuting your phone or also via the chat window.
Thanks, Bhaskar. Sorry about that. I was taking myself off mute there. But I did want to thank the presenters again today, Michael Stowe with Advanced Energy, John Podak with Fostoria Process Equipment, and Mike Chapman with Heraeus Nobolite. And, of course, thank you to EPRI for hosting the webinar. And as Bhaskar mentioned, you can certainly ask any questions at this time if you'd like, or type them in the chat box. We do also want to remind everybody that we have additional training available if you visit www.ihea.org. You can take a look at all of our training events. We also have materials and resources that you can purchase in our store. And the next webinar that will take place is in January. It's actually the fundamentals of combustion, and the information is up there on your screen now. So registration is available. If you're interested, please jump on there and register for that webinar. And other than that, I appreciate your time today, and thank you for your attendance. Bhaskar, did you get any other questions on the chat or anything else we need to address?
So I'm looking at the chat window, and there are no other questions. Anybody on the phone, you have any questions for the speakers? And just for your convenience, I have displayed the email address and contact information for the presenters. So if you have any questions that you think of, just send an email to us or to the presenters directly, and we'll be very happy to answer them. While you gather your thoughts around the questions, we would also like to remind everyone that EPRI is hosting a conference next year in August called the Electrification 2018 Conference, and more information about that will be sent via email communication. And this is a conference where we are expecting more than an audience of 1,500 throughout not only U.S. but also around the world, and looking in different electrification technologies, and a lot of utilities will be participating, as well as some of the OEMs and the customers. You could also go to electrification2018.com for more information, and more information on that will also follow shortly via email communication. So, any additional questions, or anyone have any questions? If not, we would like to thank IHEA and all the presenters for the wonderful session today, and also thanks to all our attendees for taking time out of your schedule and joining us today this afternoon. We wish you a very happy holidays and a happy new year, and we look forward to seeing you in another webcast very soon. Thank you, everyone, and have a good day.